we will continue about the relationship between potential energy and internal conservative force that we were discussing last time, including the general relationship when the force is three-dimensional, okay, or three or two-dimensional, whatever, and the usage of the partial derivative concept. So we'll do a few examples based on that. Okay, before we come back to more questions based on application of work energy theorem. Okay. So the relationship between between potential energy and internal conservative force. Let's take a relook at that. So what we had understood last time, that is, in general, if the internal conservative force is like this, okay, and a small displacement of, or a differential displacement of dx I cap plus dy j cap plus dz k cap is made, then during the small displacement, the change in potential energy is negative of work done by the internal conservative force. So it is minus of F dot ds. Okay. So this expression becomes this. Okay. So from this relationship here, we can see that if you want to invert this relation and find out fx, fy, and fz, then you have to apply this concept here that fx will become like limit delta x tending to 0, okay, minus of delta u by delta x, but under this special condition that delta y should be 0 and delta z should be 0. Okay, so that is nothing but negative of partial gradient of u with respect to x. And similarly, the terms for fy also, by similar logic, it becomes minus del u by del y, and fz becomes minus del u by del z. Okay, where these are called the partial derivative. So the term del by del x, it is partial derivative with respect to x. Partial derivative with respect to y, etc. So this is just a quick recap of what we had discussed in the last lecture. Now let's look at some application concept of this further. Okay. So next example we'll see of partial derivative concept. Samarth, you have already seen this in the last lecture. Okay, so this is, don't need to note down the whole thing again. Okay. Now supposing we have a situation where the particle Okay, so this is the formula for the potential energy of the particle given. Okay, where x, y are in meters and u is in joules. Okay. So first of all, calculate the internal conservative force acting on it. So there are no non-conservative or external forces. Then find its acceleration. Okay. So this is what we have to calculate over here. So let's look at this question. So to begin with, the concept you will use here is that potential energy here you can see is a function of xy. Okay. Because the particle is in a two-dimensional motion. Okay. So that means the internal conservative force will have only two components. Okay. Where this and Fy is minus del u by del y. So use this to find out the force. Okay. I'll just give you a quick hint that when you differentiate something like this, okay, so make use of chain rule. So okay, so make use of these steps for the differentiation here. Okay. So remember, partial differentiation means when we are partially differentiating with respect to x, we will treat y like a constant. And when we are partially differentiating with respect to y, we will treat x like a constant. So use that concept over here and come up with the derivative, rather the partial derivatives, and calculate the formula for force at a general position x comma y. Okay, so let's look at the application of partial differentiation here. So the potential energy function is, okay, or so if the internal conservative force is Fx I cap plus Fy j cap, okay, then Fx is this. So Fx becomes like this, and by a similar method, Fy so here you will differentiate with respect to y, treating x like a constant. So when you do all that, this is what you will get. Okay. So now combining these two, you can see the force will be becoming an expression like this. Okay, so make a note of this first of all. Now the other thing is units. So because potential energy was in joules with xy in meters, so here the force will be in newtons provided x and y are in meters. This expression. Okay. So now use this for the second part where you want to calculate the acceleration of the particle at 3,4 meters. So work this out quickly, people. Yes, that's correct, Samarth. So let's first see the force in vector form at this point, and then we can calculate the acceleration. The second part, at the position 3, 4 meters, the internal conservative force will become like this. In newtons. Okay. So now we know that external force is 0. Non-conservative force is 0. So the net force on the body, that only is the internal conservative force. And that will become mass into acceleration. And mass is given to us as 1 kg. So the acceleration vector itself becomes this. Okay. And if you want to calculate its magnitude, okay, yeah. So Devansh, your answer is correct for magnitude. So if we are giving the answer for acceleration in vector form in I cap j cap notation, this is the one, and the magnitude of that becomes this. Okay, so hope this question is clear, people. Now let's move on to another type of question, which is like the inverse of this. Okay, in this question, the formula for potential energy was given and we had to calculate internal conservative force. Now let's take a question where the reverse of that is there. We have some kind of force and we have to first of all show that it is conservative and then find the potential energy related to that. So suppose a force acting on a particle moving in a 2D xy plane is given by this expression. F is equal to yeah, Piyush, that is correct. That is one way to show that it is a conservative force. Very good, that's correct, Piyush. So if the force is given by this kind of relation, that it is alpha into yi cap plus x j cap. where F is in newtons and alpha is a constant in Newton per meter. So first of all, you want to show that this force is conservative. And secondly, find a formula for the particle's potential energy at a general point xy, given that potential energy at 0, 0, that is at the origin, is 0 joules. Okay, so if we are given this expression, how we'll find the potential energy relationship? Yeah, now just coming back to your point, Piyush, yes, in general, we have the curl method and we'll discuss about that also. But we'll come to that a little later because that is only required for very complicated situations. At the JEE level, the type of questions you will get, you don't need to actually go into the depth of curl level to show that the force is conservative. You can just show that the path integration is independent. I mean, the work done is independent of path by sort of normal substitution in the integration. It's usually possible to show that. And from that only we can show the potential energy function also. Okay. So generally speaking, for these type of questions, we don't need to get into curl. We can just use the normal concept that try and prove that the work done is independent of path and work done in a round trip is 0. So for that, just the critical step will be when we are doing the integration of force over displacement, F dot ds, the substitution step is going to be the critical one. So I'm coming to that next. Okay. So just take down the question, we'll discuss. Okay, so start with this. So for the first part, I want to show that the force is conservative. Okay. So we want to show that so that means the work done by this force, that is integration F dot ds, this should be path independent. Okay. So let's see how that happens. So work done by this force will now become like this. It will be alpha into y dx plus x dy from some initial to final position. Because here Okay, and so we are substituting this information here. So you get this? Okay. Now the next step is that how do we do this integration without a particular path given to us? So that is where a trick comes in now. Now the trick is that you notice this quantity, it is the derivative of some kind of term of x and y. Okay. So if we substitute some new quantity z, let's say as product of x and y, then dz will become how much? X dy plus y dx by product rule. Okay. So is this step clear? Here we're just using product rule. We're using this principle that derivative of uv is uv prime plus u prime v. That concept. Okay. Very good, Viraj. Okay. So now you notice that this quantity is nothing but this. Okay. So we can do this substitution here. So therefore, substitute z as product of x into y. So y dx plus x dy will just become dz. And let's say we are going from some initial position, which is xi to some final position, which is x final, y final. So this whole thing becomes this. Okay. Now integration of dz is nothing but this, another indefinite integration. So this next becomes now remember that z was substituted as what? X into y. So resubstitute that, and in this put the limits. So the work done by this force is just given by the very simple relation so now you can see that this work done is independent of path. Okay. Because as you can see, its value depends only on final and initial positions. So it's path independent because it depends only on position. Okay. And also in a round trip, that is closed loop path, okay, where x final, y final is equal to x initial, y initial. In this kind of a path, what will happen? The work done will be zero. So in a round trip, the work done is zero. So that shows to us that the force is conservative because it satisfies both the necessary conditions for a force to be conservative. So that is the first part. This is how we show that this force is conservative in nature. You just make a quick run through of this. Then we'll come to the potential energy. Now, once you've done this integration also, now with using the substitution step, the next thing becomes very easy. Because remember, potential energy will come from the formula of work done only. Because delta U is negative of work done by internal conservative force. So you don't really have to do anything extra. You will be using these same steps, but you will be calculating the negative of work done instead of work done. That's the only difference. Yeah. Yeah, Shikhar, because without doing that substitution, we cannot integrate. If I don't do this substitution, the point is how are you going to integrate this? No? I have this integration of y dx plus x dy. If I don't substitute here and reduce it to a single variable, then I'm going to integrate this. Okay. Now, next, what am I going to do? Because y is a different variable, x is a different variable. No? I cannot take y outside here because y is not a constant. Y is a variable. X is also a variable. So without a substitution, I'll be stuck at the integration now. You understand the point, Beta? Yeah, we cannot do that here because of that reason. Good. Okay. Now let's see how we can develop the formula for potential energy. Now that's pretty simple, especially because we are given the reference point also that the potential energy at the origin is 0. So second part, we want to calculate potential energy at a general point x comma y, given that potential energy at the origin is 0. So we just use this formula that delta U is negative of work done by internal conservative force. That means final potential energy at any point minus initial potential energy at some point is negative of F dot ds from initial to final. Okay, now we have already seen in part 1 that work done by this internal conservative, work done by this particular force. So for potential energy, we treat that force only as internal conservative. This was given by the formula alpha into this, this formula. So we don't need to do this integration again. We just substitute this here. So this becomes minus alpha into, so this is basically, you can just reduce it further by taking the minus sign inside like this. So this is the general expression for delta U. Okay. Now in this, just substitute this information. Okay. So this will become U at some general xy minus U at 0, 0. Okay. Is alpha into 0 minus xy. And this term is given to us as 0. And this term is what we are trying to calculate. So potential energy at a general point x comma y becomes minus alpha xy. Okay. So now you can see that the formula of potential energy that we have got, it agrees with the value of force that is also given to us. Okay. So you can also check that for U equal to minus alpha xy, the internal conservative force should be like this, where this should be minus del U by del x. So it should be minus del by del x of, okay, so that will be nothing but alpha y, and so to just differentiate this term, treating x like a constant with respect to y. So f will become, which is correct. That is the one that we got. So we come in the full circle. Yeah, whereas from starting the part 2 is here only. Okay. We wanted to find the formula of potential energy at a general point xy, given that the potential energy at the origin is 0. This was the question. Find the formula for the particle's potential energy at a general point x comma y, given that the potential energy at the origin is 0. Okay. So that same information here. You want to find the potential energy at xy as a formula given this information. So that is coming out to be this finally. Okay, so hope this is clear. Okay. Now we will come back to the relationship between force and internal conservative force and potential energy and define a new operator in this. Okay, so this is going to be something new for us. We'll define something called gradient operator, okay, which is a vector operator. So as we have discussed before, okay, in one dimension, gradient is just defined as d by dx. This operator is defined as gradient. Okay, so we say that f is minus du by dx in case of 1D. Okay, so it is said that the force is negative gradient of potential energy. Now this idea we want to extend it to 3 dimensions here, or to the general vector notation. So we define a new operator which is given by this symbol, an inverted triangle. Okay, so this is the symbol for the gradient operator. It's a vector operator, okay, also called del or nabla. Yes, that's correct. The symbol in Greek is called nabla. Just like you have alpha, beta, gamma, lambda, those kind of symbols. So like that, this is a symbol, the symbol name. But yeah, when we have a vector symbol on top of that nabla symbol, then it is read as the del vector or the gradient operator. So this is given by this kind of definition. It is gradient with respect to x into I cap plus gradient with respect to y into j cap. So more importantly, let us understand the application of this gradient operator. So when, let's make it 3 dimensional, sorry. So we have to add another dimension. So when operated on a scalar function, yes, absolutely. Maxwell's equations in electromagnetism are expressed mostly in terms of gradient operator. Okay. But it applies in mechanics also, not just electromagnetism. Okay, so applies in classical mechanics a lot, in quantum mechanics a lot also. Schrodinger's equation, etc., has this gradient operator. So when operated on a scalar function, of x, y, and z, okay, the gradient of this function is a vector quantity, okay, such that its individual components will be the partial derivatives of that function with respect to x, then y, and then z. So when operated on a scalar function like this, a function of x, y, and z, the gradient of the function, this is how we read the term del f. What we pronounce as del f is actually called gradient of the function f. So the gradient of the function is a vector such that the x component of that vector is partial derivative with respect to x. The y component of that function is, or the y component of that vector is the partial gradient with respect to y, and z component is partial differentiation or partial derivative with respect to z. So collectively, this del f quantity, it is called the gradient of the function f. Yeah, just write this down, Ranak. We'll understand this with examples and it'll become clear. Okay. So it is a new definition for us. The gradient operator is given by this formula. And when we operate it on a function, it gives us this vector quantity here. Okay, so just write this down for the moment. When I explain with some examples, it will become clear. Okay, so let's pick this up. So for example, suppose we have a function like this. Okay. And we want to find the gradient of this function. So this is how we'll do this question now. So the gradient operator applied to this function will give us because we know that the gradient operator is defined by this. Okay. So when we apply this operator on this function, it will give us this quantity. Yes, we just substitute if it is a complex function I mean, if you mean complex in terms of complex numbers, then you just treat the iota like a constant. Okay. Now, when you're calculating the gradient of this function, just take, with respect to x, you're doing partial derivative. So treat y and z like constants. So if you treat y and z like constants here, this term, its derivative just becomes x square. Oh, sorry. It becomes 2xy. Now, y is a constant and x square is differentiation with respect to x. So that will be 2xy I cap. The second term here, y cube z square's derivative with respect to x will be 0 because you're treating y and z like constants. Now, similarly, in the middle term, you're taking partial derivative with respect to y. So you have to treat x and z like constants. So treating x like a constant, this term will just become x square. And treating z like a constant, this term will just become 3y square z square. Okay. And again, treating, sorry, this term should be z. So here treating x and y like constants, the third term will just become 2y cube z k cap. Right. Okay. So when I'm doing partial differentiation with respect to x, you have to treat y and z like constants. When I'm doing partial derivative with respect to y, you have to treat x and z like constants. When you're doing with respect to z, you have to treat x and y like constants. Okay, so in the first term, you're treating y and z like constants. X is the variable. In the middle term, you're treating x and z like constants. Y is the variable. And in the third term, you're treating x and y like constants. Z is the variable. So that's how we get this. So that's it. So this now becomes the gradient of the given function. This is the meaning of the term gradient. Of that function. Okay, so hope this example is clear, people. Now coming back to force and potential energy. Internal conservative force and potential energy. Now our definition becomes that since delta U is negative of work done by internal conservative force, so the inverse of this relationship becomes that this is negative gradient of potential energy. This function itself implies that yeah, of potential energy. Okay, so just work this question out quickly. Yeah, that's correct. Very good. So here we'll see that once again, just use the definition that F is negative gradient of potential energy. That means the X component of force. So it is okay. So likewise, if you calculate this with all the steps, this will come out to be this. So you can see that collectively you can write the force as like this. So this should be a final answer. Yeah, sorry, there's a minus sign here. That's correct. Just make a correction, people. Yeah, Samar, thanks for pointing out. There's a minus sign in the force. So Shikhar, is the calculation clear for the point 2, 2, 1? Okay. Okay. Yeah, I understood. So now you've understood the correct way of solving, right? Okay. Okay, so this is a bit of an sort of, advanced application of potential energy and internal conservative force, the gradient concept. So you will find these type of questions in some of the JEE Advanced question banks. You will not find it in H.C. Verma chapter because H.C. Verma concentrates more on the application of work energy theorem rather than this. But in future chapters of H.C. Verma like gravitation and electrostatics, you will see that there are applications of this thing. So it is important for us for both, questions directly from work energy in JEE advanced level, as well as, things that will be based on this concept we will learn in future chapters, especially electrostatics and gravitation. Electrostatics and gravitation will come for you in class 12th. So that's why this concept is additionally important, because it's going to be important in those particular chapters also in understanding the basics. Okay. Okay, now, so we're basically done with all the theory concepts of work energy. Now we'll concentrate on some of the trickier type of applications of all this, including applications of work energy theorem. So let's come back to some examples and applications of work energy theorem. So we'll now be in the process of winding up this chapter. So also, next lecture, we will discuss your doubts also from both the module exercise as well as HC Verma. So start, winding up your problem solving of work energy chapter, so that you can be prepared with the doubts by the time we come to the next lecture after today. So anyway, coming back to examples of application of work energy theorem. Okay, statement of work energy theorem, you know that work done by external forces plus work done by non-conservative forces in general is the change in kinetic energy plus change in potential energy, where delta U is defined as negative of work done by internal conservative forces. Okay, and of course, for isolated systems, that is systems for which work done by external force is zero and work done by non-conservative forces is zero. Change in kinetic energy plus change in potential energy is zero. Or we can say that the sum of kinetic energy plus potential energy is constant. That is why the change is zero. So this statement, as you know, is called conservation of mechanical energy. So conservation of mechanical energy obviously applies only to a situation where the work done is zero. This total work done on the left hand side is zero. So let's look at some examples of this. Okay. Now, as we were discussing earlier, that sometimes the constraint relations become important in these type of situations. Okay. So the next example we'll start with is one where we will involve a constraint relation. Okay. Just a moment, people. I'll share that file again. So there is like a small particle of mass 2m here. Thread is going around another pulley. And there's a particle of mass m over here. This pulley is attached to some kind of a ceiling over here. this length is L. So initially, the particle B is being held at rest such that the threads are taut and the section above is horizontal. Now B is released. So you want to calculate the speed of A and B at the instant when A is about to hit the wall. Okay. So just note down the question. We'll understand this in detail. So this is actually a JEE question from quite a few years back. So it's an interesting question because a lot of concepts will be included in this. So obviously assume that threads are massless and inextensible and the pulley is fixed and smooth. So the first thing you need to understand is the moment you release B, what will happen? Because of A's weight, A tends to come down. But remember, A is attached by a thread of fixed length to this point on the wall. Okay, and that thread remains taut always. That means what kind of path A will describe? A cannot come down vertically because its distance from this fixed point on the wall where the thread is attached, that has to remain constant. So A's path will be what type of path? A's path will be such that its distance from this fixed point on the wall where the thread is attached, that is of L only. So its path has to be which type of path? It has to be a, yes, very, very good, Samad. It has to be a circular path. So A will be in vertical circular motion. Yes, that's correct. It will be one quadrant of a circular motion. Shikhar, that's correct. Okay. So A has to be in circular path about this point where the thread is attached to the wall. But as A moves in that circle, it will pull the other thread. No? So that will pull B up. Now this part of the thread will remain vertical. So B's path will be what? It will be vertically straight line, whereas A's path will be circular. So that is the important thing to understand now. So once you understand that path, next is you also understand that it will have variable accelerations now. So we can't really use kinematics to calculate the velocity. We have to use work energy theorem. So we'll have to use work energy theorem to solve this. Yeah, I'll explain. Okay. So see what happens the moment you release B now, because of A's weight, it tends to immediately start with a downward acceleration like this. Okay. But what is happening because this thread is of fixed length. So about this point, E will have to describe a circular path. So E's path will start rotating like this because of the tension in the thread, which will provide the centripetal force. E will describe this kind of a quarter circular path before it hits this. This will be the path of E. just before it hits the wall, it will be here. Okay. So on releasing B, okay, E will describe a circular path in the vertical plane about the point O, because that thread length is constant, and as it does that, B will describe what kind of path. B will go up. Okay. So now let's also understand that at the instant when this is about to hit, what is exactly happening? Okay. So A has taken the path from here like this. Okay. So when A is about to hit the wall, just at that moment when it's going to impact the wall, its velocity will be horizontal, because the string connecting A to the point O is vertical, and B will have a vertical velocity. Okay. So remember, A's mass is 2m, B's mass is m. Now suppose B has climbed through a height of h. Now obviously A has come down through a height of L from here. So from this situation to this situation, if you take the system as this, actually plus gravity also, then change in kinetic energy plus change in gravitational potential energy is zero, because there is no external force doing any work. There is no non-conservative force doing any work. Okay. So half 2m VA square plus half m VB square. This is the change in kinetic energy. Okay. Then minus 2m GL and plus mg h is equal to 0. So this is the change in potential energy of A. This is the change in potential energy of B. Okay. This is the change in kinetic energy of A. This is the change in kinetic energy of B. So now to solve this, we need two more equations. We need to find out the value of H. That will be our second equation. So do that geometrically. Conservation of thread length. And we also need the ratio of VAS to VB. So you can do that by virtual power or thread length, whichever you like, or the constraint relation. So just note this down and try out this now. How will you find the value of H by constraint of thread length remaining constant? And how will you find out the relationship between VA and VB? Easiest method for that will be virtual power. Okay, so nobody has got the values of y and the constraint relation yet. Let me explain. It's pretty simple really. It just comes from the geometry of this triangle. Okay, so see here in the first diagram, if this length, so we've already written as L. Now if this length is some L1, okay. So this total thread length is how much? L plus L1. So this is constant. Okay. Now in the second diagram, this in this triangle, this is 2L and this is L. So what is this thread length becoming? It's becoming root 5L. And here this is L1 minus H because it's come up by H. So H कितना होना चाहिए? Root 5L minus L. Na? So now this root 5L plus L1 minus H should be the same thread length. No? Should be the same constant. Yes, very good. That's correct. So that's this. This will tell us that H is root 5 minus 1 into L. Okay. Next thing, the constraint relation. So for that, you can just use virtual power. Okay. So on the particle A, you can see that the direction of the velocity is like this and tension is like this. Let's say this angle is theta. So that's the same as this angle theta. So power delivered on A by tension is minus TVA cos theta. And on the particle B, so minus TVA cos theta plus, so VB should be equal to VA cos theta. Now in the diagram, you can see that is at that particular instant, the value of cos theta is based upon hypotenuse. This relation and this relation will be substituted in equation 1. So M VA square plus half M VB is equal to yes, you can just check my final calculation here, but this is the method of solving. Okay. Yeah, Prachi, for H, see what we are doing is now compare the two diagrams, the above one and the below one. So in the above diagram, the thread which is connecting A and B, इसका total length I have written as this. L plus L1 is the total length of that thread, let's say capital L, which is a constant. Okay, that is a thread connecting A and B. Now in the below diagram, A is now here. So it stretches out this thread into this hypotenuse. So the length of this hypotenuse becomes root 5L. In the same time, B has gone up by H. So this length from A to the pulley is root 5L, whereas from the pulley to B is now L1 minus H. So the total of this thing should be still capital L, which is the same constant. So equate this length with that one. And from that, you will get H as root 5 minus 1 into L. Is it clear, Prachi? Yeah, so that half has been cancelled, na, Samar? That's why I've got 2 by 5. No, but your beta wo thread alag hai na? The one which is connecting the point O with A, that length L is over here. That's the vertical section. I'm concerned with conserving the length of the thread joining A and B. So that's why it's L plus L1. You know? Right now? Okay. So that gives me the value of H. Now constraint relation is simple, virtual power method you can use here. So this constraint is coming from virtual power. Okay. Yeah, now Samarth, in this step, na, this is 4 by 5, but there's a half outside. Na, so, whereas here this was 2m. This mass is 2m na, of E. That's why. You just copy from here. Yeah. Okay, so hope the calculation part is clear. This question will be there in one of the solved examples in your reference books, because this is one of the classic questions from IIT. So in these type of slightly advanced type of questions, your constraint relation becomes very significant along with the statement of work energy theorem. Which is why when we are discussing constraint relations in Newton's laws of motion, I told you that it's something important in entire mechanics. This is a JEE Advanced level question, obviously. Okay. That too, like better level question from JEE Advanced, not the average level question of JEE Advanced. This is a better level question. Okay, so people, with that we conclude today's session. So as I said, we are done with the theory part of work energy. So next lecture will be discussion of more problems and discussion of some of your doubts. Okay, so continue working on work energy applications. Complete HC Verma if anything is pending, including the questions of vertical circular motion. Vertical circular motion, I think we have done along with circular motion. Anyhow, in the next lecture, I will be discussing some questions based on that also. Don't worry. But the standard derivations from vertical circular motion, like the condition for root 5 GL in the case of a thread attached with a particle, completion of vertical circular motion, things like that, make sure you revise. So it has application of concept of work energy as well as of course the circular motion concepts. Okay, that and then other questions of work energy, theorem application, as well as gradient, potential gradient, being internal conservative force being negative or potential gradient, those kind of things. So please work out maximum questions and be prepared with your doubts in the next lecture. That's it for today, people. Wish you all the best.